Hello and welcome to our next video. In this video we're going to be analyzing vertical compressions and expansions. Let's take a look at our first example. Describe the transformation necessary to obtain the graph of g of x, the dashed line, from the graph of f of x, the solid line. So in this case, our blue function, it's our f of x. That's our original one. And our new one, it's the green dash one, which is g of x. In particular, we know that g of x will have the form c times f of x because we are dealing with vertical transformations. In this case, we're going to think of this as a particular force that it's pushing our blue parabola down in the vertical direction so that it gets distorted to the extent that it starts to look more like the dash green parabola. Now, to figure out what is our constant value here, what we can do, we can choose a particular integer value of g, so we can have the corresponding output value along with the corresponding input value. In this case, what I'm going to do, I'm going to choose this point from the actual curve g of x, okay? I'm going to identify my output value, which is 2, and my input value, which is 2 as well. So in terms of my input, I can see that I'm going to use 2 for my x. So I'm going to say I have g of 2 is equal to c times f of 2. Now, in order to solve for c, I need to come up with the actual value for g of 2. G of 2 happens to be 2, so I have 2 is equal to c times f of 2. If I go to f, for the input of 2, I can come up and say, okay, this happens to be 4. Now, to solve for c, let me go ahead and divide by 4 on both sides. This implies that c is equal to 2/4, which can be simplified to 1/2. Now, since c is 1/2, we notice that c is greater than 0, but it's less than 1. Since this is the case, we have what we refer to as a vertical shrink. Now, in the context of compressions and expansions, we can describe the transformation as simply a compression, okay? So we can say that in order to get from f of x to g of x, what we need to do is the following. We need to compress vertically by a factor of 2. Okay? You can think of compressing as telling you, okay, I want the reciprocal of that particular c value. In this case, the reciprocal 1/2 is 2. Okay, that's why we have a factor of 2 here. Let's see another example. Example 2. Describe the transformation necessary to obtain the graph of g of x, the dashed line, from the graph of f of x, the solid line. So here I have my f of x, and I also have my g of x in green in this case. Okay. In this case, we can think of as the following. Okay. Before, in example 1, we were kind of pushing down. Now here you can think, okay, now maybe we're pushing this one up to distort it and eventually make it look like the green parabola. So we are having a vertical transformation. Therefore, we can say that g of x is of the form c times f of x. Again, what we can do in order to figure out what is the value for c here, let's go ahead and find any point on g of x that has integer coordinates. In this case, I'm going to choose this point, okay, which will have an input value of 1 and an output value of 3. So I'm going to choose x to be 1. So I'm going to substitute in value of 1 for x. So I have g of 1 is equal to c times f of 1. Now g of 1 is equal to 3, and that is equal to c times f of 1. When I have an input of 1, notice that my output for my blue parabola, it's 1. So we have that c is equal to 3. And since 3 is greater than 1, we can say in this case that we have a vertical stretch. But in the context of compressions and expansions, this is an expansion, a vertical expansion. So to describe the transformation, we can say that we need to expand vertically by a factor of 3. Make sure that 3 looks good for you. Okay? Now let's see 2 more examples here. Example 3. Describe the transformation necessary to obtain the graph of g of x from the graph of f of x. Here we're given that f of x is equal to x squared and g of x is equal to 1/3 of x squared. Let's go ahead and identify our constant here. C is equal to 1/3. And notice that 1/3 is greater than 0, but it's less than 1. Okay? So here we have a vertical shrink. But in terms of compressions and expansions, we can describe this transformation as a compression. Okay? So we would say, in this case, let's compress vertically. And remember, compress, we're going to take the reciprocal of this by a factor of 3. Okay, so let's see one more example here. Lastly, example 4, describe the transformation necessary to obtain the graph of g of x from the graph of f of x. Again, f of x is x squared. G of x in this case happens to be 3x squared. So let's go ahead and identify our constant here. C is equal to 3, which is greater than 1. Okay, so we can say that we have a vertical stretch. But in the context of vertical compressions and expansions, this will be an expansion. So to describe the transformation, we would simply say something along the following lines. Let's just expand vertically. So let me write that down. Expand vertically by a factor of 3. Okay, so notice that's our constant in this case. When we're expanding, we don't take the reciprocals, we just take the value for c directly. Okay, so that concludes our video on vertical compressions and expansions. I hope you enjoyed, and I would like to wish you a wonderful day. Thank you for watching. See you next time.